Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find area of the green shaded square? Take a moment to study the figure. Then, let us uncover the key geometric ideas that make the solution click. The green square EBFD sits inside right triangle ABC, and all six source labels A, B, C, D, E, and F are part of the construction. We need the area of square EBFD. The square lives inside right triangle ABC, and the right angle is at B. That single right angle is what makes the two legs perpendicular, which we will lean on again and again. Corner B of the square sits right on the right angle, so side EB rides out to the right along leg segment BA, and side BF rides down leg segment BC. That means the right edge segment ED runs parallel to leg segment BC, and the bottom edge segment DF runs parallel to the leg segment BA. The far corner D of the square lands on the hypotenuse segment AC, cutting it so that segment AD is 7 and segment DC is 14. These two lengths are the only numbers we are handed, so the whole solution must flow out of them. Let X stand for the side of the square, so the edges segment ED and segment DF both equal X. The area we are chasing is X squared, which turns the whole task into a hunt for a single number X. The square carves the big triangle into three pieces: the square itself, a small triangle to its right, and a small triangle below it. Those two corner triangles are where the given 7 and 14 will do their work. To the right of the square sits the small triangle AED, sharing the square's right edge segment ED. Its short leg segment AE extends to the right along the horizontal leg toward corner A, and its hypotenuse is the given length segment AD equal to 7. Below the square sits the small triangle DFC, sharing the square's edge segment DF. Its long leg segment FC stretches downward along that leg toward corner C, and its hypotenuse is the given length segment DC equal to 14. In triangle AED, the right edge segment ED meets the square side EB at a right angle, and A lies straight to the right of E on that same side. So the angle at E, angle AED, is a clean 90 degrees. The same reasoning holds below. In triangle DFC, the side DF meets the left leg at a right angle, and C lies straight down that leg past F. So the angle at F, angle DFC, is also 90 degrees. At corner D, the two square edges segment DE and segment DF meet, and being a square, that corner is 90 degrees. This 90-degree wedge sits right on the straight hypotenuse, which is the key to the next step. Points A, D, and C are collinear. After the right angle square at D uses one right angle, the two acute angles ADE and FDC are complementary and together make 90 degrees. Inside triangle AED, the right angle at E leaves the two acute angles DIE and IDE complementary. Together they make 90 degrees. Angle DAE and angle FDC each complete the very same angle ADE up to 90 degrees. Two angles that fill the same gap must be equal, so angle DAE equals angle FDC. Aha! Both corner triangles are right, and the two remaining acute angles match because each completes the same 90-degree angle at D. Those complementary angles force triangles IED and DFC to be similar, pairing hypotenuse segment AD with segment DC. Before reading any ratio, we must pair the vertices correctly. The right angles pair E with F, the equal angles pair A with D, and that leaves D paired with C. Getting this order right keeps every ratio honest. The paired hypotenuses are segment AD equal to 7 and segment DC equal to 14, a ratio of 1 to 2. Every pair of matching sides in these similar triangles must share that same 1 to 2 ratio. Side AE in the right-hand triangle matches side DF in the bottom triangle, and segment DF is just the square's side X. Applying the 1 to 2 ratio, segment AE equals 1/2 of X. That is the last unknown we needed in the right-hand triangle. Triangle AED is right-angled at E, so the Pythagorean theorem applies. The hypotenuse segment AD squared equals leg segment AE squared plus leg segment ED squared. Remember, segment ED is a full side of the square, so segment ED equals X. Now put in what we know. Segment AD is 7, so segment AD squared is 49. Segment AE is X over 2, and segment ED is X, giving 49 equal to X over 2 squared plus X squared. First, tidy the squared term. Squaring X over 2 squares, both the top and the bottom, which gives X squared over 4. That is the fraction we will now combine with the whole X squared. Write the lone X squared as 4/4 of X squared, so the two terms share a denominator. 1/4 plus 4/4 makes 5/4, so the right side collapses to 5/4 of X squared. Aha! We do not need to solve for the side X and then square it again. The equation already solves the square area X squared directly, so the next step can read off the target without an unnecessary square root. To free X squared, multiply both sides by 4/5, the reciprocal of 5/4. That gives X squared equal to 4/5 of 49, which is 196 over 5, or 39.2. And X squared is precisely the area of the square, since area equals side squared. So the green square's area is 196 over 5, with no square root left to take. Now confirm with the other triangle. Segment FC matches segment ED at the 2-to-1 ratio, so segment FC is 2x. Pythagoras in DEFC gives 5x squared equal to 196, so x squared is again 196 over 5. So the area of the green square EBFD is 196 fifth square units. That completes the solution. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share it in the comments. Even a rough idea is welcome. A sketch of the key move is enough. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.